All right, this is Calculus Section 5.2. We are finally on to the last part of this section, Part 3. All right, so it says here first, if we look back at the example 3 from yesterday, what happens whenever you take the limit as n goes to infinity of the lower and upper sums? So if we go back and look on page 9, you can see here I've got these equations for my upper and my lower sums. One thing I want to point out, and I didn't catch yesterday, but I could have reduced this 12 over 3 and turned it into a 4 over n. So if I were to do that, you can see here then I have those exact same equations here for my upper and my lower. So if we go through now and we want to find the limit as n goes to infinity, now we're looking back at our infinite limits like we did last chapter. And we know here, if I'm taking and I am plugging in an infinity into n, and I take 4 divided by infinity, this term is basically going to be a 0. Same thing here with this n squared. It's going to be a 0. And all I end up with here is the 8/3. Same thing then is going to be true over here. If I were to find the limit as n goes to infinity, this 4 over n is going to go to 0. This 4 over 3n squared is going to go to 0. And all I'm left with is this 8/3. And since we know that our limit, or our actual area was going to be somewhere between these two values, somewhere between the lower guess and the upper guess. And if we end up getting the exact same value for our lower guess and our upper guess, we could use the squeeze theorem to say that this 8/3 is going to be the exact area underneath that curve. So if we look here at limits of lower and upper sums, it says here to let f be continuous and non-negative on the interval a to b. The limits as n goes to infinity of both the lower and upper sums exist and are equal to each other. So what that's saying here is I've got the limit as n goes to infinity of my lower sum. My lower sum was the summation from I equals 1 to n of f of lowercase m sub I times delta x. That's going to be the same as when we take the limit of what our summation formula for our upper sum was, and this upper sum was denoted by S sub n. So our limit of our lower sum is going to equal the limit of our upper sum. And again here, where delta x is found by taking b minus a and dividing by n. So that's going to be the width of each of these rectangles. And f of lowercase m sub I and f of uppercase m sub I are the minimum and maximum values of f in the subinterval. So then next now we're going to take a look at the definition of the area of a region on a plane. So here it says to let f be continuous and non-negative on the interval AB. The area of the region bounded by the graph of f and the x-axis and the vertical lines x equals a and x equals b. So, and actually before we even look at this here, what this is saying is that you have to have all of your curve above the x-axis for what we're talking about today to hold true. So everything's above the x-axis. We're finding our area to the x-axis and then in between two x values, a and b. Says the area is going to equal the limit as n goes to infinity of the summation I equals 1 to n of f of c sub I delta x, where the c sub I is going to fall in between my our two values here. So here it shows the c sub I falls in between an x sub I and an x sub I minus 1, and our delta x is going to be the same b minus a over n that we had before. Now on this, we're going to end up finding this c sub I pretty much the same way that we found our m sub I whenever we did this last lesson. So if we want to add here, we can think of it almost like formula-wise for the c sub I. This is going to be a being whatever our initial start point is here. And then it's going to be plus I times delta x. So our width, and then this I here, as we plug into our summation is going to catch the first rectangle, the second rectangle, the third rectangle, and so forth. And the thing is since we're taking this out to infinity, and we know that our upper sum and our lower sums are going to be equal whenever we evaluate it, it means that we don't have to worry about this I minus 1 to go back to the left endpoint like we did before. We can assume these are all right endpoints. All right, so go ahead and flip over to the back side. We have two examples we're going to take a look at. This first one here says example 1. Technically, it should say example 2 because example 1 was whenever we revisited example 3 from the last section. All right, so for this, again, just a reminder, our area formula that we're working with now is going to be the limit as n goes to infinity of the summation from I equals 1 to n of f of c sub I delta x. So for this problem here, we're finding the area of the region bounded by the graph of f of x equals x cubed, the x-axis, and the vertical lines x equals 0 and x equals 1. And here's a picture of that. We can see here that's the curve x cubed from 0 to 1, and then this rectangle they have in here shows then where my c sub I would end up falling, and so forth. All right, so first thing that you need to do when you do problems like this is we need to figure out what our c sub I is equal to and what our delta x is equal to. So if I start with delta x, I know that my change in x is always going to be b minus a over n. In this case, my b and my a is 1 and 0. So 1 minus 0 over n, which is just going to be a 1 over n. Then, if I go and find my c sub I, that's going to be the a plus I delta x, which in this case, my a, or my starting value here, is at 0, so it equals 0, plus I times delta x, which my delta x we found to be a 1 over n, which then would just simplify to an I over n. And now we're going to go and plug those two values into our formula for our area. So we need to find the limit as n goes to infinity of the summation from I equals 1 to n of f evaluated at my c sub I, which is I over n, times my delta x, which is a 1 over n, which is going to equal the limit as n goes to infinity, the summation of, or from I equals 1 to n. And now here, if I plug in an I over n into my function, x is getting cubed, so I need to cube this I over n. So it's going to be I over n quantity cubed times that delta x, 1 over n. Now, this then is going to equal the limit as n goes to infinity. And on here, just like we were doing before, these n's, even though it's going to infinity, it represents a constant. And the only thing that you want to leave inside of your summation here is going to be the i's. So if I were to take and cube this I over n, I would have an I cubed over n cubed. And I could take this n cubed and combine it with this n over here to make a 1 over n to the 4th. And then that 1 over n to the 4th can come outside of the summation. So 1 over n to the 4th. And now I'm going to put my summation from I equals 1 to n. And all that's left inside now is going to be this I cubed. Now I can, from that paper we had the other day that had all of our summations on it, we can pull the formula for the summation of I cubed, which real quick right here it is. I cubed is an n squared times an n plus 1 quantity squared over 4. So we still have the limit as n goes to infinity. I still have this 1 over n to the 4th. But now I'm going to replace this summation here with the formula, which was an n squared times an n plus 1 quantity squared all over 4. And now we're just to the algebra part where we're going to do all of our simplifying. We're going to break this into individual terms like we had on the front side so that then we can take the limit as n goes to infinity. All right, so we are going to have, first off, this n squared and this n to the 4th will reduce to just make an n squared here. So this is going to be the limit as n goes to infinity. This then now reduced to a 1 over n squared. And then here, I'm going to go ahead and multiply and distribute out what an n plus 1 quantity squared would equal. I've got an n plus 1 times another n plus 1. The n times the n is going to make an n squared. I'm going to have an n times a 1 and then another n times a 1 to give me a 2n. And then a 1 times a 1 is just a 1. All over 4. This is going to equal then the limit as n goes to infinity. I'm going to now distribute this 1 over n squared at the same time that I break this thing up into 3 separate fractions over 4. So here that would make an n squared. And then on the bottom, this n squared times that 4 makes an over 4n squared. Then I have a plus. 1 times this 2n is going to make a 2n on top. On the bottom, n squared times a 4 makes a 4n squared. And then the last one, this 1 times this 1 is a 1. This n squared times this 4 makes a 4n squared. And all of this now I'm taking the limit as n goes to infinity. And on here now you can see this n squared and this n squared will cancel. Here, only one of these n's will cancel. And whenever this n on the bottom goes to infinity, this entire term here is going to go to 0. Because any number divided by infinity is basically then a 0. Nothing cancels on this last term here, so when I plug in an infinity on the bottom means that this term is going to 0, which means all I have left is this term here, which is a 1/4, which means that the area underneath this curve, x cubed from 0 to 1, is going to equal a 1/4. All right, last example, example 3. We are finding the area of the region bounded by the graph f of x equals 4 minus x squared in the x-axis and the vertical lines x equals 1 and x equals 2. So again, I'm going to go ahead and write down, we know that area is going to be the limit as n goes to infinity of the summation from I equals 1 to n of f of c sub I delta x. And then we need to, just like last time, figure out both what my delta x is going to equal and what my c sub I is going to equal. So on here first, my delta x is that b minus a over n, which in this case, my b and my a is a 2 and a 1. So 2 minus 1 over n, which is just a 1 over n, just like we had on the last one. However, my c sub I is going to end up being different because for this one, that a plus I delta x My a is no longer 0. This time I'm starting at 1. So this is going to be 1 plus I times a 1 over n, or just a 1 plus I over n. So this one's going to look slightly more complicated when we start plugging stuff in because of this 1 plus I over n. All right, so next then, we need to go through and put in our c sub I and our delta x, evaluate with our formula, do all of our reducing and simplifying to figure out what the area is. So this is going to be the limit as n goes to infinity of the summation from I equals 1 to n of f evaluated at c sub I, which is 1 plus I over n, times delta x, which is a 1 over n, which is equal to the limit as n goes to infinity of the summation from I equals 1 to n. And now here, if I plug in this 1 plus I over n into my original function, it's going to look like a 4 minus the quantity 1 plus I over n squared times my delta x, which is a 1 over n. All right, so now what we're going to need to do is start distributing here, doing all of our simplifying. I know, again, this 1 over n is basically a constant, so I'm going to pull that out and then do my distributing here with this binomial. So this equals the limit as n goes to infinity. I'm going to pull that 1 over n out in front of my summation. So then I have the summation from I equals 1 to n. And now here I have my 4. It's going to be a minus, and it's minus this thing distributed. So first off, a 1 times a 1 is going to give me a 1. Then a 1 times a I over n, and then another 1 times an I over n is going to make a 2 times an I over n. And then an I over n times an I over n is going to make an I squared over n squared. Then we're going to need to distribute this negative sign through these terms. So this is the limit as n goes to infinity. And the thing is as we're doing this, I know it is extremely tedious to be going through each time and writing this limit as n goes to infinity, but it is important and necessary because we haven't taken the limit yet. So you have to keep writing it each time until we get to that last step where we're actually plugging in infinity for my n's. So the limit as n goes to infinity. I still have a 1 over n. I've got the summation from I equals 1 to n. This is going to be a 4. That's going to distribute to make a minus 1. Here what I'm going to do is I'm going to distribute to make that a minus, but here I'm going to pull this 2n away from this I so that I have a single I that I'm going to be plugging in from my summation formulas from the other day. So minus 2 over n times I, and then same thing here. I'm going to take this 1 over n squared and pull it in front of the I squared. Distribute the negative, makes a minus 1 over n squared times I squared. And now we're at a point where we can go in and do all of our substitutions. So I'm going to start a new line because it's kind of lengthy. We want now the limit as n goes to infinity of 1 over n. No longer do we have a summation because when we plug in from our formulas, we've evaluated with this sum. So the 4 minus 1 is going to make a 3. And the constant rule is you just multiply by an n. So that's just going to be a 3n. Then I'm going to have a minus 2 over n. My formula for I I is just an n times an n minus 1 over 2. So an n times an n plus 1. I think I maybe said minus 1 a second ago on accident. N times n plus 1 over 2. Then I have a minus 1 over n squared. And then my formula for the I squared is the n times the n plus 1 times the 2n plus 1 all over 6. So n times n plus 1 times 2n plus 1 all over 6. And now it's time for us to get in here and start simplifying some things. So I'm going to, first thing here, these n's will reduce and these 2's will reduce. Here, one of these n's will reduce. I'm going to have to do my distributing here. So I'm going to just to kind of save some space on paper, right above it what all this would be distributed out. So an n times a 2n is going to make a 2n squared. An n times a 1 and then a 1 times a 2n is going to combine to make a 3n, so plus 3n, and 1 times 1 is 1. All right, so this is going to be the limit as n goes to infinity. Here I still have my 1 over n. I've got my 3n. Here this negative will distribute to the n and to the 1. So it becomes a minus n and a minus 1. Here, this n will go with this 6, and then I'm going to break up each of these terms. And don't forget, we also have this minus. So it's going to be a minus 2n squared over 6n. Has the minus here distributed to the 2. This n went with the 6. So again, now this minus is going to distribute to the 3n to make a minus 3n, and on the bottom here, that's going to distribute to make a over 6n. And then the last one here, this minus is going to distribute to the 1 to make a minus 1 over, and then the n and the 6 to make a 6n again. And then the last bit of distributing that we're going to end up doing is we're going to have to take this 1 over n and distribute it to everything. Before I do that, I'm going to go ahead and do a little bit of simplifying with my n's now, because I know that these n's will reduce, and I know that one of these n's will reduce. All right, so this is going to equal the limit as n goes to infinity. When I distribute this n to this 1 over n, to this 3n, the n's will cancel and I'm just going to get a 3. When I distribute it to this n, the n's will cancel and I'm just going to get a minus 1. When I distribute this 1 over n to the minus 1, I'm going to get a minus 1 over n. When I distribute this 1 over n to the 2n, the n that's left and the n on the bottom will cancel, and it's just going to leave a 2 over 6. Then here, when I distribute this 1 over n to the 3 over 6, I'm going to get a minus 3 over 6n. And then this last one, when I take this 1 over n and I distribute to this 1 over 6n, I'm going to get a minus 1 over 6n squared. And now my last step is I'm going to go through and go ahead and evaluate that limit. So this over n is going to go to 0. This over n is going to go to 0. And this over n squared is going to go to 0. And all that's left is this 3 minus 1 minus 2/6, which is 1/3. 3 minus 1 is 2. 2 minus 1/3 is 1 2/3, which is the same as 5/3. So for this problem then, the area underneath this 4 minus x squared from 1 to 2 is going to be 5/3. All right, so that one wasn't quite as long. Hopefully you are able to see in these problems the pattern. It's going to be the same thing every time. The hardest part is going to be the simplifying stuff in the middle to make sure that you don't mess up a number or something somewhere. But every time you do these, you're always going to end up following this area formula, which in order to follow the formula, you're going to need your delta x and your c sub I. Your delta x is always going to be your second point minus your first point over n. Your c sub I is always going to be your first point plus an I times whatever your delta x was. You're always going to take that c sub I, plug it into your formula, times your delta x. And also what's nice, this delta x, I don't know if you noticed on this one and the one before, but it will always be able to pull out in front. So really you're just working with your function. So you do all of your simplifying within your function, then you replace all of your i's with your summation formulas, you do all of your simplifying until you get to the end and you get a bunch of terms that are going to end up going to 0, and all you're left with are numbers to combine. So you guys have problems to practice with this on page 300, numbers 45, 47, 49, 51, and 53. You need to get in and practice these problems so that you have somewhat of an idea of what you're doing. We will come together next class period and talk about questions that you guys have, and then you are going to be doing a review worksheet after this where you're going to be able to partner up or small group with some people. We'll small group, social distance, but we'll work through these problems together. And then what's going to happen is there's going to be individual groups then that will come up to the front of the room, and you'll actually teach your problem to the class. So everyone's going to be responsible for all 5 problems, but you're only going to be responsible for becoming an expert on one of those 5 problems so that you can teach it to others, and then we can check to make sure that everybody got the right answer. So if you have questions on any of this as you're working, feel free to shoot me an email, let me know. Otherwise, work on these overnight, come back to next class period, and ask what questions you have.